So welcome to all members in the audience and to my colleagues who are the participants and organizers of the conference, The Impact of Artificial Intelligence on Contemporary Design. And thank you also to Jaël Eilat van Essen and Arnost Marx for putting this informative and kaleidoscopic program together. During the next hour, we will listen to and learn from the ideas of three panelists who were brought together under the headline Consciousness, Authorship, and Intelligence. And I think it is actually very interesting to listen to all the presentations in this conference, taking, for instance, into consideration that we are all creative and intelligent people who grew up in the pre-internet era, and somehow each in our own way and with our own interests and viewpoints, likely influenced by culture and locality, evolved towards the integration and utilization of these new technologies that we are discussing today. Some of the participants actually briefly mentioned this evolution, be it from having studied architecture, design, or art, which I assume, based on the example of my own educational background, was still mostly rooted in traditional approaches to such disciplines, to the so-called post-human era, in which we try to find solutions to design problems that were previously unknown and perhaps even non-existent. So when technologies advance, human behavior changes and design and art react to it, which again has an effect on human interaction and which possibly informs and optimizes the potentiality of new technologies. And I believe that some of the speakers in this panel will suggest sort of a way out of this cycle, perhaps by proposing scenarios that outsmart non-human intelligence in ways that can only be human, or by creating artworks similar to rainbow unicorns, which I found absolutely amazing, as presented by Eyal Grus, and which I would like to propose to the organizers as the title for their next design conference. So the three lectures that we will attend after this introduction are about to begin. Mr. David Faitelson will speak about conscious machines. Mr. DesAIgn about authorship in the age of generative architectural design. And this panel will be concluded by Ms. Maria Tsilogiani on the subject of artificial idiocy. So our first speaker is David Faitelson. He studied in Tel Aviv and in Oxford, and currently he's a senior lecturer at the Afeka Academic College of Engineering. And he is also enrolled in the integrated design course at Holon Institute for Technology. His research includes the application of formal mathematics to the construction of correct software, computational biomimicry, parallel programming languages, and the design of intelligent robots. David, if you are ready, then we are looking forward to your speech on the subject of conscious machines, why we should fake it.
Hi, hello everyone, and thank you for this wonderful, wonderful conference. I'm enjoying the lectures very much, and actually I was hoping that the last question in the Q&A would, Eyal would pick it up and answer, because it would be a great starter for my talk, but it was left open. I hope everybody can see the question, because it's really about my bringing it into my first part of my talk. But we'll see. Maybe the discussion would happen afterwards. So I want to actually say that in the first part of my talk, explain why computing machines, even though we've seen these amazing things they can do, really they are not and will never be neither conscious nor intelligent. But then I would like to argue that we can actually, it would be beneficial to when we are designing the new kinds of autonomous and smart machines that we're beginning to see today, it would be actually beneficial if we design them to behave in ways that we see as conscious, as if they are conscious creatures, and then how all this affects the role of the designer of such systems. And I'll try to refer to some of the earlier speakers, because I think they've said many relevant things that are related to what I'm going to say. So, I mean, we are now in the middle of a very big hype wave around artificial intelligence, and we can see why, because some of these new technologies, they're really very, very successful, and they're creating very useful things and interesting things. But I think some people have gone way too far with kind of extrapolating from what they see, and you get people, for example, implying that our minds are essentially algorithms, and therefore it's possible to write better algorithms and to create better minds on the computer, and you know, soon we will be replaced by machines. And of course, this discourse has been picked up by the general public, and we've seen in the last, I think, 20 years, many movies and other like books about these topics. The latest one is this funny animation about a dysfunctional family that's trying to save the world from an evil smartphone. So, but I would like to argue that this is not going to happen, and that in fact, machines are not conscious, and they will never be conscious. And while there are very many good arguments supporting this point, and I've listed some of them at the reading list at the end of my talk, I want to give an argument that's coming from the heart of computing science, because I think that not a lot of people are familiar with it, but it sheds, I think, a very important light on the nature of computation. So if you think about all the computing machines that we have, that the old ones and the new ones, the big and the small, you know, the quantum computers and the computers that we haven't built yet. But if you just strip away all the technology from the computers, all the ways that are being used to create them, and you just look at the essence of what it means to compute, you can reduce all of this into a single mathematical machine that we call a Turing machine. And the Turing machine is a very, very simple machine. All it has is this tape, and on the tape, it can write symbols and read them. And it has a table, and the table tells it what to do. So here it's beginning in this position, and it sees a B, and the instruction is to replace it with an A and move right. And then it will do that again. This time, the instruction is telling it to move to the left, so it will return back. But now it's in a different state, so it has different instructions. And so it comes back. And basically now it's at the same point it started, and it will go again. And you can see this process will repeat itself forever. So it's just replacing A's with B's. A meaningless exercise in symbol manipulation, that's it. And here is a different example of a machine that appears to be doing something more useful. Now, if you're familiar with binary notation, you may see that what's going on here on the tape is that the machine is adding 3 and 3 in binary notation, and by the time I finish talking about this slide, it would produce the correct answer to the left here on the tape. But what I want to emphasize is that really the machine isn't doing arithmetic. The machine doesn't know anything about numbers. It doesn't know anything about addition. What the machine is doing is it's processing just a different table. So from the point of view of the machine, these are just 2 tables, and the machine is happy to do one or the other. the meaning of what's going on is in our heads. The meaning is in our human understanding of what numbers are, of what is addition, of what is arithmetic. From the point of view of the machine, all the tables are equivalent. And it's very important to emphasize that this is just any kind of computation, anything that you can program on a computer, even on Google's cloud computers, any kind of fancy neural network algorithm that you will come up with can be reduced to this kind of table running on this very, very, very simple Turing machine. So I think actually that if you want a good analogy for what a computer is, then it's much more a record player than a brain. So if you take a Guns N' Roses record and you put it on the record machine, you will hear rock music. Take a Mozart symphony and put it on the record machine, you will hear classical music. But the record player isn't listening to the music. The record player is indifferent. He doesn't understand the music. So saying that you know, a computer, that there is a table that if you put it into the computer, the computer will suddenly become conscious or intelligent, is a bit like saying there is a record that if we put it on the record machine will come alive, will become conscious. But of course, this is, it doesn't mean that these simple manipulating machines are not useful. So if you have a phenomena that you understand very well, like you have a good model for how water flow and geometry of light, how it reflects from water, you can create very useful simulations of water. So here on the left, we have a simulation of water, and on the right, we have actual water flowing. And you can see that they're kind of similar, but what's going on in both cases is very, very different. What happens on the left is that we have a machine that's doing an enormous amount of calculation to figure out for each droplet of water where it should go, solving differential equations. But of course, the water, when it flows, it doesn't need to solve differential equations in order to know where to go. It just flows. So these are two completely different phenomena, even though if they look the same. And actually, I think that when we're creating a successful artificial intelligence system that using some of the techniques that we've seen earlier, we are very much in the same position as a magician, a good magician, because in both cases, we are creating in a very, very controlled environment, a very powerful illusion. And it doesn't mean the illusion is bad, but we shouldn't be fooled by it. It's just an illusion. Of course, like when we come out of a good magic show, we don't conclude that magic is real just because the magician fooled us and we don't understand how we did these tricks. So now I would like to kind of switch over and say, okay, so no, it's not really conscious, it's not really intelligent, but how can we fool ourselves in ways that would be actually beneficial to us? Because obviously we've seen examples where you can, I mean, it's possible to fool us, and it's quite easy actually to fool us in harmful ways. And I would like to focus on the kind of new machines that we're starting to see these days, and we've seen examples about self-driving cars earlier, and I think that's it's very relevant. So the computing power has become so powerful that we can run these very, very demanding computations, you know, almost everywhere. I don't know how many, like, so you're familiar probably with the USB chargers that we're using to charge our phones. I don't know how many of you know that there are computers inside these chargers. And inside some of these chargers, you have computers that are more powerful than the computer that took the Apollo 11 to the moon. So really, we have this enormous computing power, and we see that we can start to create things that are autonomous, that can do things of their own, and they have an internal complex state that we cannot see, governed by a computer. So I think it's useful to kind of look back and see how we got to this point. And when we started creating tools, they were very passive objects. We had to control them directly, and they had no autonomy whatsoever. So the design language was very simple. It was basically just, you know, tell me where I should hold the broom and what is the part that is cleaning the dust. And everything else was done by us. When we moved to creating, sorry, when we moved to machines that have a bit more autonomy, so like this vacuum cleaner, it can suck the dirt by itself, but it doesn't know where to go to clean the room. We had to create a new communication language to control the device. But now we are creating things like this Roomba or self-driving cars or robots in assisted homes and things like that. And we want them to behave autonomously. We don't want to babysit them. We want them to do their things without bothering us. And this requires a change in our design language. And I think, I would argue that the Roomba is a kind of transition object, in the sense that it's a new kind of machine, but its design is still rooted in the old machines. So the heart of my argument is that a good model for looking at autonomous and smart machines is an animal, a creature, because, I'm sorry, I'm losing my voice. Because an animal has, like a smart autonomous machines, both animals and machines, they have a complex internal state that we cannot see, but we need to be able to understand what's happening with them, and they have goals that they are achieving autonomously or mostly autonomously. So we can learn from the way animals communicate how to create effective communication with these kind of smart machines. And if you look at the way animals communicate, we see that this is mostly by gestures, by movement, and not by symbolic means like we do with language. So I call it behavioral communication. And actually, if we remember that we are part of the animal kingdom, then I think it's important to see that we have, I would say, these two kinds of communication systems. We have the new communication system, which is written language and speech, and the old communication system that we are sharing with all the animal kingdom. And you know, the new communication system, speech is about 1 million years old, and language is about 4,000 years old, alphabet, I mean, and written language. But the old system has been around for almost 1 billion years. So it had much more time to develop, and therefore the information processing bandwidth of the old system is much wider than with the new system. And as a result, we process information much faster here in the old world versus the way we process information in the new system. So reading and writing and even in spoken language takes a lot more cognitive effort than the enormous amount of information that we process that is not symbolic, that is coming from our heritage as part of the animal kingdom. And I would argue that it's so efficient that we don't even notice that it exists. But I mean, think about like the experience of walking down the street, navigating obstacles, assessing the intentions of other people and animals around you, the wind, the temperature, the humidity, all this amount of information is being processed by us, but we don't even notice that we're doing that because this is such an efficient system. Whereas, I mean, if we start texting, we become immersed in the device. All our cognitive powers are being directed to it. That's why it's so dangerous to text while you're driving. So, so if we want to communicate effectively with autonomous machines without being immersed in them, because then we lose the whole benefit of using an autonomous machine, then I think we should adopt the old communication system rather than using the new. And I guess, I mean, using the new communication system is kind of expected because the computers are symbol manipulators. So it kind of makes sense to speak to them in their language. But I think computers are now so powerful, they have enough processing power to be able to understand the old communication system, to mimic it. And when they mimic it, this mimicry creates in us an effect as if the machine is intelligent or conscious. Now it's an illusion, of course, but it's very useful because it's much more efficient and it's much less annoying and distracting for us. So Donald Norman wrote this wonderful book, The Design of Future Things, and he talks about the idea of a natural interaction between us and the new kind of machines, where the interaction is that of continual awareness, but of each other's activities without the annoyance. And he says, if you want to design self-driving cars, you should look at the relationship between a horse and its rider. And I think what I'm saying about behavioral communication, about communicating with the machines, not through symbols and text and the new system, but through gestures, through movements, through sounds and things that are concrete, is really natural interaction. And just to illustrate this point and what it means in terms of design, I want to show you this, this nice work from university in Canada, University of Manitoba in Canada, where they took a Roomba. I hope you can see the video. So they took a Roomba, and what they did is that in order for it to communicate its internal state, they've attached a tail to the Roomba. Now you can see it's a very crude attachment. Certainly they didn't try to redesign the Roomba from scratch with behavioral communication. But I think it's, and it's also funny, I like it because, I mean, there are more serious works about this topic, but this is really, I mean, it makes me smile, so I put it here. So what's going on here, I think, is very important in terms of design, because the tail is not needed for the functionality of the machine. The Roomba doesn't need the tail in order to clean the room. The tail is explicitly created for communication, to communicate the state of the machine to us. And immediately when you see it, and when people saw it in the tests that they did, immediately it becomes much closer to a living, conscious, maybe even intelligent creature, even though it's very, very crude. And I think this is what I'm trying to say about the role of design for these new kind of machines, is that as a designer, it's no longer possible just to be satisfied with designing the static form of the machine. But if we want to create this effective communication, we need to create also the dynamics of the machine, not for the functionality, but for the communication. So if a robot cannot find a part it needs, it can act as if it's confused. If a self-driving car is, its battery is beginning to run low, it could act tired. And things like that will move us towards a much more effective and I think the idea of trust came here, and trust, I think, is essentially a lot about me being sure that the machine understands what I want, and I can also understand what the machine wants. So this effective communication is essential for trust. And so I'll conclude, because I've run out of time. You know, computers, they are just record players that manipulate symbols. You can give them sophisticated tables, but they're still record players. And we can use this notion of an animal as a model for designing smart objects, smart machines, autonomous machines, giving them behaviors that for communication, not just for functionality, escaping the screens and the displays and the text. And I think that could create the kind of effective and efficient communication with these machines that would actually make them useful to us in relieving us from having to babysit them and be immersed in their interfaces. And so, yeah, and so the designers should be able to design this behavior, this dynamics, not just the static form of the machine. So that's it then. That's my talk. Why can't I hear anyone?
I apologize. I just realized my microphone was muted.
I was trying to figure out why I can't hear anybody.
I was wondering, like, to what your proposal can lead, not only in terms of design solutions, but also in let's say the field of human interaction with these smart machines.
Well, I hope that when we are approaching the design of these smart machines, we will be able to go beyond the idea of a flat screen with symbols on it, and the design the machines. So the communication shouldn't be basically just a large iPhone. The communication should be. There's a wonderful work about. There is a growing field of robotics called cobots, which are robots that cooperate with humans to perform tasks in industry, for example. And it's very important when a human is working with a robot that the robot will not kill the human, because the robot is very powerful, and if it moves without the human being, without the human paying attention, it could just kill the human. So you need a lot of trust, and you need a lot of awareness for these two kind of entities, and having the human operator constantly stare at a screen is not effective, because he couldn't do his job. So if the robot has a kind of sign language, a gesture language that it can show by its behavior what it's about to do, then you can start. Then the human will not be afraid to work together with the robot. And I think this also is important for design of things like self-driving vehicles. So for example, today, when I'm about to cross the road and the car approaches, I look the driver in the eyes, and I create this non-verbal communication with the driver, and I build trust that he understands that I am about to cross the road. So we need something like that for autonomous vehicles, because if now the vehicle that's approaching has no driver inside, how am I going to build this trust to know that it's safe for me to cross the road? I need this kind of form, and to look at the self-driving vehicle as a creature, and to give it a language, a non-verbal language, a behavioral language that would be clear to me, because we understand, because this language of gestures is common to all animals. We can build on that because we understand it also intuitively very easily. So so it's kind of, I'm kind of suggesting here to use a form of biomimicry for the communication between us and the smart and autonomous machines, and not necessarily try to think of these machines as in anthropomorphic sense, because actually we really, very far away from understanding the human mind, and our attempts to create machines that behave as if they are human are really, they are not working. They're creating, I think, the opposite. They are creating this kind of, I don't know, there's a term, I forgot the term, uncanny valley. And this creates mistrust. It's the opposite of trust. So because we intuitively feel we're being conned. It's not a human, so don't try to mask as one. Why are you trying to mask as a human? So.
Yeah. Sort of as a side note, because the example of the Roomba sort of struck me, and I think it is definitely an interesting field to further explore in for instance, what way young children look at this tool, this device, which is ultimately still a vacuum cleaner. Yeah, that's why I was actually happy to see the image of a broom, especially in this type of conference. Like, let's go back to the old very basic tools for that purpose. But I'm afraid also that we are a bit running out of time. But it is definitely an interesting subject to understand more about young people's interaction with these kind of newly invented tools and smart machines, how they perceive it, and how they actually have their own type of interaction with it.
So David, there's a very interesting question here, but I'm afraid I don't have to answer it. So maybe I'll just type my answer. But I don't know if, because I understand that not everyone can see the questions.
Yes.
What do you suggest me to do?
I believe we have 2 minutes for this question.
Well, so the question is, why do I believe that over 60% of some 350 AI experts in a recent survey believe technological singularity is approaching? I don't think that we need to talk, about beliefs here. I think we have to look at, what we are building. And I think that, a lot of these experts are not, I'm not familiar with them, but all the people that I know in the computing science community would never think that anything even remotely, similar to singularity is about to happen anytime soon. Quantum computers are just, another technology that's making some computations faster. That's it. There aren't any little mindlets inside the quantum computer that create something that doesn't exist in the Turing machine. It's still a Turing machine. But maybe maybe it's I don't have time to answer it more deeply. I'm sorry.
Let us indeed conclude with this because we're running short in time. David, thank you so much once again.